audible? Like you can drop a yes in the chat. I'm little uncertain with all the online meets. Cool. Yeah. Thanks. Like I will be like discussing this architecture unit. It's based on unit and unit plus plus, which is a version of unit that got scaled up. It's based on semantic segmentation. So I'll be rolling through everything mostly like from the start is not much I assume, but in case there's any doubts, you can always drop them in the chat. Cool. So this is what you're going to be covering, like two simple semantic segmentation architectures, unit and unit plus plus. Working knowledge of CNNs is assumed, and resonate and related architectures, if you have an idea of how they're implemented, that is a bonus. And slides will be available after the talk, so links and everything will be available afterwards, so that you can access the material freely. So let's move on. Like this is where it starts. Semantic segmentation is basically, I'm just covering this a little bit. It's a process in which we try to classify every pixel in an image into a category. So for example, this image of like a lane is given, and we've classified, if you can see this image, we've classified every pixel in this image into a certain category. So all the reds over here, the darker reds are all vehicles, the greens are all vegetation. As you can see, there's a legend given down here. So this process from here to here is semantic segmentation, and well, this is used in a variety of places. We already saw one, autonomous vision systems to make better driving decisions. The other one that it's found a lot of usage in is biomedical imaging. So for example, this is an example that's taken from the original unit paper. This is cell tracking. So basically given an image to find out where the cells are and kind of draw a border around them. This is useful in a lot of tasks. In a lot of places, it is necessary in medical imaging that we understand where cells are and where they are moving, so that we can track the growth of cells, any cancers that might be possibly growing, and so on and so forth. So this is a very important task in these two areas. It is widely used in other areas as well, but these are the two most important areas in which semantic segmentation finds a huge amount of use. So we'll go to the task and we'll break it down. So each pixel has to be classified. So the output, so in a traditional CNN, when we are doing image classification, one of the things that's very simple is that the input is an image and the output is a set of numbers that denotes like the probability of an image belonging to a certain class, right? Like say all of you must have worked with like data sets like Cypher 10. So it's pretty simple. You take an image and the output is basically a set of numbers that each denote the probability that the image belongs to a particular class, a car, a plane, and so on and so forth. So what are the similarities of image classification with semantic segmentation? Both of them need to make use of feature extraction. And what I mean by this is that all images have certain features. So for example, in the previous example, like if we go back 2 slides, over here you could say that these cars are all features in this image. You could say that if you're looking at finer details, you could say that each of these license plates is also a feature. But one of the things that is common between image classification and semantic segmentation is this idea of extracting features from the image. And this is where convolutional neural networks are so good. They extract features from the image. And then, of course, for the purpose of classification, we introduce fully connected layers at the end and kind of get them to output probabilities that the image belongs to a certain class, right? But over here, there's a difference. We do want to extract features. We do want to know whether a certain feature is there in an image or not, so that once we know whether a feature is there or not, only then can we go about classifying its pixels. And the output is a segmentation mask. So each pixel is being classified into a class. So if we go back here, we can consider each of these to be a class. The buildings are all a class of pixels. The sidewalk is a class of pixels. The road is a class of pixels. The pole, the vehicle, and so on. Each of these is a class, and So over here, the output is 2D, and instead of image classification, where we were just outputting like a set of numbers, over here we need to output the probability that the pixel belongs, each pixel in this image belongs to a certain class. So instead of outputting it for the whole image, for each pixel. And that's the major difference between semantic segmentation and say image classification as a task. So this was the first major deep learning approach in semantic segmentation. This is called fully convolutional networks. And this was the first approach to use convolutions throughout. There were no fully connected layers in this entire thing. And this makes sense because fully connected layers are required only in image classification, only because you want class outputs. Over here, you do not need class outputs. All you need is an output image which has pixels classified into certain classes, right? So the other major contribution that this made is it suggested an encoder decoder type structure. So I'll go into this in a little more detail further down the line, but a brief understanding of what this means is the encoder is a set of layers or a first architecture that basically takes your image and extracts all the features from it. Like I said, this is where CNNs are really good. They extract the features really well, and any CNN architecture that works for image classification without the fully connected layers can be used as an encoder. So any of your classic architectures like AlexNet or ResNet or VGG, without the fully connected layers that are basically for classification purpose, if you just take the top off, so to speak, these all can be used as encoders because they are really good at extracting the features from the images. And then there is a decoder type architecture. Now we'll go into detail about what this decoder type architecture looks like in a couple of slides. But the basic idea behind this is that once you've extracted all the features, you have all the information that you want in feature space, then you need to find a way to go back to 2D outputs, right? You want to be able to output the probability that each pixel belongs to a certain class. So for that, we're going to be using this decoder type architecture from going from this feature space back to like a higher dimensional space where you can have these class probabilities. And this is where they use transpose convolutions for upsampling, and these are all learnable parameters. So everything that we will see in the next slide is differentiable. There is no hand engineering for anything, for any upsampling or anything, except kernel sizes. But all of this has been all the parameters are differentiable, so you can just backprop through the entire network and it will learn everything. So first, before we go into transpose convolutions, we look at convolutions as a matrix multiplication. This is important because to understand where the word transpose come from. So if you look at this is basically an image that I found online. This is a very nice picture. You can see that this dark 3D grid is the kernel. If you imagine this to be the kernel, and if you imagine this lighter blue uh, grid to be the image, you can see that the kernel is like shifting over the image and producing this two-dimensional output on top. All right, you can see this. So now if you imagine that the input, like you imagine that this is the kernel, it's actually these are the elements of the kernels, like W00 is the 0, 0 element of the kernel, and so on and so forth. And if you write this as this sparse matrix, this is sparse because there's a lot of zeros in this. And now if you imagine that you completely unroll the input and output vector. So the input vector is a 4x4, this light blue. You completely unroll it into a 16 cross, like completely flatten it out, then multiply it by this sparse, and you get a like a 4 element vector that's flat. And then you reshape it back to a 2x2. That 2x2 will be this output vector. Sorry, this output matrix. So basically, if you look at it, we are able to represent convolutions as we saw over here as a matrix multiplication. So the process basically involves first forming this sparse matrix, then you completely unroll the input vector completely, like after completely unrolling, you multiply this, you get a completely unrolled output vector, which you then reshape, and after reshaping you get back your output matrix. So this is how you can represent convolutions as matrix multiplications. and this is used in some frameworks for implementing convolutions as well. So over here is the first time that we can understand where the term transpose convolutions comes from. So if the matrix C, like we saw C over here, if this matrix C defines the forward pass, then C transpose represents the backward pass. That is, like when we are back propagating through this entire network, I hope that you are familiar with these terms. The local gradient, the C transpose will be the local gradient that will be multiplied by the upstream gradient while back propagating. So I think most of you have done the Andrew NG course, and there might have been a link to a Karpathy article which described why learning backprop is important, or something of the sort. They and even the course, I think they make use of these terms, local and upstream gradient. So the local gradient at that point is C transpose, and the upstream it is multiplied by the upstream gradient while back propagating. So this is nice. We can prove this by matrix calculus. I'm obviously going to leave that for any of you to do at your leisure. But what this means is a kernel which defines a convolution whose forward and backward passes are C and C transpose. So W is the kernel, C and C transpose are the matrices that we saw over here, the unrolled, these gigantic matrices, unrolled. And these define a transpose convolution whose forward and backward passes are C transpose and C. So if you can consider this is basically the exact opposite of the convolution operation if you think of it in terms of just in the context of this image processing, right? If you're instead of going C and C transpose, you're going C transpose and C. So this is somewhat of an opposite to the convolution operation, which is something that you will want to upsample from feature maps to segmentation maps, and this is exactly what we use. This is why it's called transpose convolution. Instead of using C, instead of multiplying it by C, we multiply it by C transpose, hence the term transpose convolutions. This is just a note. These are often called like up convolutions, deconvolutions, fractionally strided. For mathematical details, this PDF is basically the best PDF I have come across in my life for convolution arithmetic. It has all the formulae. It has some really cool GIFs in the GitHub repo if someone wants to check that out. And it has like a really nice way of explaining everything. And for still further cool information about deconvolutions, there's a Distill article about deconvolutions in checkerboard artifacts, which if someone is interested, you can just read that. I attached that for good measure. So we have understood what transpose convolutions are, and transpose convolutions are what FCN, that is the fully convolutional networks, use for upsampling. So now let's take a look at the architecture of that. So this is the FCN architecture. I have deliberately not like gone into much detail in this because this is a very obsolete architecture. It's mainly just there for historical purposes. So this part of the architecture is basically the encoder. If you can look at this, and you can see this happening, the 224.224.3 image is going in, and you're basically doing what a regular convolution network will do right up till here. So you've extracted all the features that you possibly could up until you get up to a 774096. Like if this is typically the point where you say like we've had enough of feature extraction, and you flatten everything out and start adding the fully connected layers. But since that is for image classification, this is where we stop. Then we start to upsample over here, and this is just transpose convolutions implemented where convolutions were. So over here it was convolutions, over here it's transpose convolutions, and you're just doing the same process over here until you get 224, which is the same size as the input image and number of classes, because you want the probability that each pixel belongs to a certain class. So the number of maps that are produced in the end have to be the number of classes. So I hope this part of the architecture is clear. This is what I meant when I talked about an encoder decoder. So if you look, there's a clear split down the middle. This is the encoder architecture. This is encoding all the features into the feature space, and this is the decoder architecture. It's decoding from the feature space back to class probabilities for every pixel. There's also skip connections that have been implemented here. For those of you familiar with like ResNet architectures, this is very commonplace. They've basically introduced some learnable parameters and a little bit of convolutions, and they've basically tried to do this skip connection from here to here. But as you can see from like the visualization of this architecture itself, it's not very symmetric. There's a lot of there's a lot of numbers that seem to be chosen by hand, and the original paper includes furthermore places where they've said we've introduced one cross one convolutions to reduce dimensionality, and it's not very symmetric or very nice. So the drawbacks of Fcn, which is that the skip connections are chosen arbitrarily, like they're chosen in just two places. There's no inherent symmetry in the structure of the network. It's not easily composable. You can't play around with this architecture much because most of it has been chosen by hand, like the numbers and so on and so forth. And one of the things that people realized after this was that the encoder downsamples a little too aggressively. So this is something I read about online. This decreases the resolution of the input by a factor of 32. So a factor of 32 decrease in resolution is like a lot. So the decoder module struggles to produce fine-grained segmentation. So if you look at examples online, there'll be examples where it shows that Fcn is not really like the best at some of the finer segmentations. It's good overall, but it otherwise struggles with like fine borders. So now we move on to unit, which is going to be the focus of this talk. Unit builds on Fcn in terms of the encoder decoder structure. So we saw over here that there was a clear split. This encoder decoder structure overall is still maintained in unit, but of course there's a lot of changes in terms of the way that these are implemented. So it introduced a symmetric structure, as we'll see in the next slide. This is easily interpretable, easily composable. You can play around with stuff. There's a uniformity in choice of kernel size and composition of layers. So the structure is very symmetric, very nice. It's completely uniform, and therefore it's something that you can play around with very easily. Tweaking parameters is not hard, and it's just overall a much better design structure than Fcn. So if you look at unit, this is the unit architecture visualized. And if you look at the image sizes, biomedical image segmentation, where the images are a lot larger. So if you look at these images, the image sizes are given over here, they're a lot larger. But if you notice the downsampling that is done, it's been much less aggressive than the original one. The factor over here, I believe, is 17 as opposed to the original 32. So that's one of the things that it does. So it improves on Fcn in the fact that it doesn't downsample as aggressively, meaning that hopefully it should be able to produce finer grained segmentations. The other thing that it does is you can see that this symmetry is inherent. This is why it's called U-net, by the way. Literally, the shape of the net is a gigantic U, and the symmetry is very inherent in the way that you can see this entire thing. There, all convolutional kernels are 3x3. All max pools are 2x2. The upcons are all 2x2, and there's something called copy and crop, which is basically over here. The skip connections have been implemented at every level over here. So first of all, let's talk about encoder decoder. This is the encoder part of the mechanism, and down up till here, round about here, and then we're transferring this across, and this is the decoder part of the mechanism. So this is the part that's transferring back from feature space to the output segmentation. And this copy and crop is basically an implementation of the skip connection, but done in a different way. Over there, if you notice, the skip connections were done like at just two intervals. Over here, if you notice, every level has these skip connections. There are 4 levels shown, and each of them has a skip connection. And these skip connections have been done pretty simply. So over here, the output segmentation maps were 388, 388, and so what they have done over here is they've taken like the same size crop from here, a central crop of some sort, and then just they've just copied that, and they've concatenated this to the output from the previous layer of this encoder mechanism. And at every step this has been done. So they've taken this crop, they've just shifted it over here, they've concatenated it, and then they've just fed it to like 2 convolutions, and then upsampled again there's a copy and crop over here. This is concatenated, then fed to 2 convolutions, and again upsampled, and so on and so forth. So this is, as you can see, this is a very symmetric architecture. All sizes are uniform, and this is one of the major reasons that this architecture was immensely popular, because it is easily composable. You can play around with the kernel sizes and stuff very easily, and This architecture was extremely successful in resolving medical imaging. It achieved state of the art at the time. So this was unit. The loss function, we'll talk about that a little bit. So the energy by energy function is what they've called. So basically, the output probabilities, and this is computed by a pixel-wise softmax over the final feature map combined with the cross entropy loss function. And this is pretty simple. We wanted to classify every pixel, so the softmax has to be over the pixels. So the pixel-wise softmax basically just says that we're trying to classify each pixel into classes and give a probability that a pixel belongs to a certain class. So one of the things that this changes is from like this is something new, which is weighted cross entropy to account for pixel imbalance. So if you look at the original image, which I will find in a second, it's right over here. Yeah, this. So if you look at the original image, this is taken from the unit paper. There's a lot of background pixels, right? So there is a huge amount of background pixels over here, and in comparison the number of cell pixels is comparatively lower. Actually this image has lesser imbalance, but if you consider certain other biomedical imaging data, there will be a huge amount of imbalance in terms of background and cells. The number of pixels in which the cells are will be really low, and the number of pixels in which the background dominates will be much higher. So one of the things that the authors of unit wanted to take into account was this imbalance in pixels. So they took something, they basically took a weighted cross entropy loss to account for this. The other thing that they did was they wanted to force the network to learn separation borders between the cells. So this is not a very demonstrative image, but there are other medical imaging like cases where the borders between cells are very close, and in order to be able to like segment or rather highlight both cells and be able to see both cells distinctly, and to be able to see like the borders of both cells distinctly, they force the network like additional parameters in this weight. So basically they're trying to enhance that part, the border part, so that they can see the separation between closed cells very easily. So if you look, these are the weights that they did. They introduced first WC. WC deals with class imbalance. This is again a function. They've given the values in the paper in case someone wants to check that out. And this entire term is for dealing with the separation borders thing. So there's an exponential in these two terms. So d1 and d2 are basically distances to the border of the nearest and the next nearest cell respectively. So those two values are taken and then fed through this entire function. So this is the weight that you are feeding in this cross entropy loss, this weighted cross entropy loss. And this weight is done for like two reasons, as we said, the pixel imbalance thing and the separation border. So this is something that is specific to unit, these weights, that is. Other papers have chosen other weights depending on their tasks. So a lot of papers, for example, will not need this separation border part, since this is specific to biomedical imaging and in particular cell imaging. So that was this. So that is about it for unit. So before I move on to unit plus plus, I just want to ask, is everyone following what I've said so far? If there are any doubts, you can put them across in the chat, like before I move on.
Hello.
Yeah.
Am I audible? Yeah. Just a small question. Do the authors mention the intuition behind like why they're doing these center crops in between?
Sorry, which one?
The architecture, if you go back. Yeah. So you mentioned they are doing some random center crops, rather not random crops. So the center crops for concatenation. So is there any major reason for doing that? Or so when the entire part?
Yeah, the cropping is because like when you're downsampling, the border pixels are lost in every image, right?
Yeah.
Yeah, so basically this cropping is to deal with that part.
Uh, okay. Cool. All right. Thanks.
Yeah, cool. Like just to be clear, there's no padding over here in most of the convolutions, which is why like to deal with that loss, like because there's no padding, the border pixels will be lost. And so they did the center crop so that the sizes would match up. Cool.
All right.
Any other doubts? Right, cool. So we'll move on. This is Unit++. Unit++ did two major improvements over Unit. The focus was on one, redesigning the skip connection. So this skip connection became a hugely important thing after these two architectures, Unit and ResNet, and a lot of other architectures came related. And practically uh, most successful neural network architectures today use some sort of skip connection or the other. So this is hugely important for facilitating information flow. It helps in gradient flow. It helps in making the optimization problem easier. And this has become more or less a staple in neural networks these days. So Unit++ focused on redesigning these skip connections for reducing semantic gap for ease of optimization. This is a term that the original paper uses. As I understand it, semantic gap basically just means, if you look at this, for example, each of these, when we're downsampling from here, like each of these. So for example, if you consider this to be completely in feature space, like you say this is 100% feature space, although like I'm pretty sure this is inaccurate terminology. So this is just for the purpose of understanding, like don't quote me or anything on this. So if you consider this to be like 100% feature space, and if you consider it to be 0% feature space and like 100% image space, so over here you're somewhere in between, right? Like say maybe you are 33% of the way towards feature space. So each of these, and when we're coming back up, you're going to this output space, which is basically like class probabilities, and you're upsampling from feature space. So semantic gap is basically what these pixels mean in, like what these pixels actually mean. So these pixels, for example, they carry some amount of image meaning and some amount of feature meaning, and these pixels also carry some amount of like feature meaning that they've carried from down here, and some amount of class probability meaning that they will eventually be moving towards. So this is how I've understood semantic gap to be, and one of the major things that they've tried to do in this paper is redesigning the skip connections for reducing this semantic gap for ease of optimization. So if there is a huge difference in this gap, this semantic gap, which means what the pixels actually mean, then optimizing these pixels, like optimizing this network can be really difficult. And they wanted to redesign these connections so that that does like that difficulty is reduced. The other thing that they've done is they've introduced dense skip connections. So for those of you who are familiar with densenet, this will be like very familiar. Dense skip connections are basically, instead of just skipping ahead like one within one block, all layers from previous blocks are connected to all layers in front, and this is basically again smooth transfer of information and improving gradient flow. So over here, this is Unit++, and this is the major this is the major architecture, and I want to talk about this image quite a bit because this is going to be like the major discussion over here. So as you can see, like this is actually the unit architecture. So from here, if you look at it, let's say we're feeding the image in here. So first you can see that xij means a convolution. So from here you're downsampling, and so if you just ignore everything in between, if you ignore this entire part, and if you just look at the outside of this looks remarkably like a unit architecture. And that's because it kind of is. It's based on unit. That's why it's called Unit++. So this entire thing is just that. But if you remember, the middle space in unit was completely empty. What these guys have done is they've made it much more denser, much more populated, and they've tried to fill it with nodes of convolutions and dense connections. And this entire thing is for the purposes that I mentioned in this. So basically reducing the semantic gap and for ensuring smooth transfer of information and improving gradient flow. So if you can look at this is the part where you're trying to reduce the semantic gap. So over here, direct crop, like direct, there was a crop over here and then concatenation. That is how like the skip connections were being implemented. So instead of that, we have all of these are learnable parameters that are given over here. So these learnable parameters are what are going to be making the semantic gap lesser. Basically, they're going to be helping you transfer from one sort of space to another, and that is why they've implemented all of these. So these are all convolutions. Like as you can see, xij represents a convolution, and they've all been implemented for the purpose of reducing the semantic gap. Now, if you look at the arrows, which are the skip connections, you can see that they're all dense. Like the connections are all, every which way, and every layer in front has connections from every layer behind. So this one has connections from these two, these ones has connections from all of them, and the feature maps are concatenated over here. So there's this big skip connection over here, and this. So every node has information of all the maps from the prior node. So this is how unit plus plus was designed. It's basically unit and dialed up to 11. It's made denser. The skip connections are made much more. It's basically done to optimize the network as much as possible, so that this network will both learn more easily, and b have much more interpretability, because you've reduced semantic gap. So hopefully it should be able to give much better masks at the end of this task. So this is the unit plus plus architecture. This is the major part of the architecture that we will be dealing with. This is one of the features that the authors have cited in unit plus plus as being the key contributions. They've added something called deep supervision, which is shown in red over here in the original figure, as you can see. And if you can see these smaller versions of unit which plus plus, which are also shown over here, you can see that there are these red lines shown over here as well. So this deep supervision is basically so that the model can be pruned to adjust model complexity, and that is to balance between speed, which is inference time, and performance. So this is something that is very unique. It was not this very few neural net architectures have this, and unit plus plus was among the architectures to demonstrate this. So for accurate mode, the output from all segmentation branches is average. So if you can see this is one segmentation branch, this is another, and another, and so on. So the output from these is average for the accurate mode. So accurate mode will take a lot of time to run, but it will give you like much better masks. And for fast mode, the final segmentation map is selected from one of the branches. So you can actually prune, which is what they've shown over here. Like this is when you're running it in accurate mode, you're taking all the segmentation masks and you're averaging over them. But depending on how fast you want this network to be, you can prune down the number of layers in it, and you can network and get very fast outputs. So this is something that they've added called deep supervision, which is something very unique in terms of architecture, neural net architectures. And this is one of the major contributions that the authors consider that they have made. So that's about the major part of the unit plus plus architecture. We'll talk about this. This is a custom loss function that the authors have designed. This combines cross entropy loss. So you can see that there's some terms, the log term, and it combines something called a dice coefficient. We'll go into dice sometime late, like soon enough. It's also called F1 score sometimes. This is basically a coefficient that is used for comparing how similar two sets are. But this is a custom loss function that the authors designed, combining the dice score and the cross entropy. And y hat b and yb are flattened predicted probabilities and flattened ground truth. So y hat is predicted, yb is this, so the ground truths, and these are flattened, and then they're fed into this custom loss function. So this is the loss function that the authors defined for the purpose of this, and this was the loss function that was like that the network was optimized on. So this is just like a note on this. So we're done with unit and unit plus plus as architectures. We'll mostly be looking at metrics next. Does anyone have a doubt in the architecture part that I've discussed so far? Any questions regarding how the architecture is made or framed or anything like that?
Can you go over semantic gap once again?
Right,
Hello?
cool. So there's a lot of disagreement. Like I should mention this. There's a lot of disagreement online on what exactly this term means, because the authors have not exactly like explicitly specified it in their paper. There are a lot of different interpretations of what semantic gap means. But the idea of semantic gap is basically what the pixels represent, like the meaning that the pixels have. So when you're trying to go over here, for example, like I show it through unit. For example, over here, if you're here, you're in image space completely. So all these pixels are representing something in the image. As you keep going down, you're moving towards feature space. So all of these pixels, all of these values are going to be representing something regarding a feature. So they're going to be mapping something in feature space. But like I said, this is a gradual progress. It's not like there is one threshold beyond which everything converts to feature space. This is a gradual progress from image space to feature space. So this is the semantic meaning. The semantic is basically the meaning that these pixels have. So the semantic gap is basically that. So if you look at it over here, these pixels are going to be carrying a certain amount of image meaning which they've carried from over here, and they are moving towards feature meaning, which is going to be ultimately over here, where they are going to be in feature space. And like I said, this process never really starts or ends, but like for the purpose of explanation, we can take it to be like that. Like say we can consider it to be somewhere between image and feature space. And over here, if you look at this, we're upsampling from feature space to class probability space. Like the output is going to be the class probabilities, right? So this is another space altogether. So we are out upsampling from here to here. So the meaning that each of these pixels has is is what is known as the semantics. Like we usually use the word semantic when there is some meaning associated. The semantic gap is the fact that there is a difference in the meaning of what these pixels mean and what these pixels mean. And so therefore cropping and concatenating them directly may not necessarily lead to the best results, which is why in unit, if you unit plus plus, if you notice, they had convolutions over here. So learnable parameters which allow you to gently transfer from like this space to this space without having like a sudden jump in what the meaning of like these pixels are and these pixels are. Is that okay?
Yeah, thank you.
Yeah, cool. So oh cool, okay, like I'll come back to this one like after I'm done with this. There's just a little bit of like part left regarding the metrics, and I'll come back to this question like, immediately after. So we just go with this part. This is common metrics for semantic segmentation. So first is pixel accuracy, and pixel accuracy is the percent of pixels in your image that are classified correctly. So this is really simple. This is really straightforward, and but this is not always the best metric because of class imbalance. So like I said, in the case with there's a lot of background pixels, and there are very few like pixels of the cell or the car or whatever it is that you're trying to like get via semantic segmentation. So there may be an imbalance in that. So if you classify every pixel correctly, while the cell may be very small, it is a very important part of the entire task. So this is, but this is a metric that is still used in for understanding like what exactly the task is doing. It can be used when there is not much class imbalance. The other metric is an Iou score. An Iou score is basically, again, this is very straightforward. Intersection over union is the area of overlap between the predicted segmentation and the ground truth, divided by the area of union between the predicted segmentation and the ground truth. So this image is very nice. It's very representative of what's going on. So area of overlap. So basically, we take the output from the network, and then we take the ground truth labels, and then we compare what is the area of overlap by just like superimposing the images and seeing how much area overlaps, and then we compute the area of union, and then we take the ratio. And this is again a very common metric. I like this image a lot because it really shows visually what is going on with this entire thing. This is like much better than pixel accuracy in terms of class imbalance, because as you can see, it's going to be paying attention to even very small objects, because the area of overlap upon union will still be a like a nice ratio between 0 and 1. And this is dice coefficient. We saw this in a couple of slides back. This is a custom loss function that they define. So the dice coefficient is just 2 times the area of overlap, which is this black region, divided by the total number of pixels in both images. And again, this is like this. I like this image a lot because it visually shows what's going on. So it's 2 times the area of overlap and the total number of pixels in both images. So this is again very representative. This is also called the F1 score in some literature, and this is also a metric that you will see being used for semantic segmentation tasks in a lot of cases. So these are the three most common metrics that you will see. So just to wind everything up, we looked at we got a high level overview of simple semantic segmentation architectures. We understood transpose convolutions in the context of upsampling. We understood that skip connections are really important for information flow, which is why Unit++ has a lot of dense skip connections to improve on Unit. We looked at Unit and Unit++ in particular to understand how symmetry and composability, which is two of the key features of both networks, are the fact that they're symmetric and they are composable, and these are important for a model architecture to be popular or useful, I should say. So thank you for this, and I will be ending the slideshow right now. If there are any questions, you can post them in the chat. I think there was already a question. Let me address this first. Right. So as for the part for how to differentiate between background cells and pixel cells, they seem pretty similar. Well, yeah, the authors actually say that like these background weight, like these weights for initially, I think were fed in by hand, if I remember correctly. Let me just check this once in the original paper. But if I remember correctly, these parts, the part about the background pixels and the cell pixels, I think the definition, if it was not designed by hand, that there was some sort of formula used where to distinguish between the two. I think, however, that these ground truth labels were just fed in by hand.
Yeah, hello. Am I audible?
Yeah.
Yeah, so just as a continuation of a question that one of the guys had asked, so you had told that the center cropping is to compensate for the pixels lost during each while passing through each convolutional layer, right? So how
Right.
does cropping help that? Like
So
cropping?
when you're so when
Go
you're
ahead, go ahead.
convolving an image, the number yeah, right. So when you're convolving an image with a kernel, the pixels lost are going to be at the borders, right? So process of convolution happening, like the image size is going to be smaller, like slightly smaller for every convolution. The output image size is going to be slightly smaller than the input image size if you don't use any padding. So if you imagine this entire process happening, you can imagine this as like that the pixels being lost are at the border. So if you can visualize this entire like process, it will become pretty apparent that the pixels being lost, the pixel information being lost is going to be mostly around the border. So that's why center cropping is basically what they've done to make sure that the sizes match up. Because
Okay, for each
if
layer we are
you
going
like
to
take away those
okay the
border parts, then the part of the image that is left after the crop is going to correspond roughly to what you obtain after the convolutions.
okay. And just one more doubt. So we cannot be sure that the whatever the cell or the required part is at the center of the image. So if it is at the edge, wouldn't we be losing required information? So wouldn't adding a padding and doing be a better implementation?
Yeah, it is, which is why if you look at many further implementations of Unit, they actually do this. They do use padding instead of like the central crop thing. This is Unit was designed for a very specific data set and a very specific task, and hence the architecture is implemented as it is. But if you look at a lot of implementations available online, like Torch or Keras or any of these, or even other implementations, or even papers that derive on the unit architecture, they don't use the central crop thing anymore. They mostly just pad and convolve, and like the concatenation or the skip connections are implemented without any central cropping, because there's no way to be certain that you're not going to be losing image like important information, as you said. This was just specific to the like the original implementation of the paper, because they implemented it on a very specific data set and a very specific task. So yeah.
Okay, okay, yeah, thank you.
One quick question.
Yeah.
Can you please present again, like the unit architecture slide?
Sure, will do. One sec. This one.
Yeah, this one. So the output map segmentation map size is actually smaller than the input image size, right?
Yeah.
So in the data set which we get for like as annotations, so the corresponding maps which we have finally, how is it obtained? Like, because via this the if image like the map size is actually reduced from the input image size, right? So if we annotate the original image
Yeah.
directly, so that would actually give me a map but which will be of the same size as the original image. So do this downsample the image, or am I missing something? Like while calculating loss and all that stuff. You get my question, right? Like what I'm trying to ask, or should I rephrase?
Which is smaller. Yeah, you're talking about this, right? Like the output sizes are smaller than the input sizes, and so therefore, how do we like compensate for that those loss of pixels?
Not exactly loss of pixels. I'm saying like for every we have like we are mapping from X to Y, right? So we need
Yeah,
Y
yeah,
as training, right? So we'll have some segmentation maps obtained while from the data set itself, like that will be a part of the data set, correct?
yeah,
So those maps will also be of size of
yeah, yeah.
same as the
True.
input
Go on.
images, right? So there's a mismatch in these sizes. That's what is confusing me. So do they
Wait, so
downsample?
if
Yeah,
oh,
go on, go.
so if I've understood you correctly, you're asking how do we match this like how do we match the ground truth labels that we already have, which will be of the original size of the image?
Right, to this final output of this unit.
Yeah, I think they mirrored pixels wherever like wherever there was loss of information. If I remember correctly, they just mirrored the pixels because, like I said, this was a very specific task. So all the most of the important information was right in the middle of like the image. So I think they mirrored pixels, but let me just check the original paper once. But if I remember correctly, they just mirrored pixels from the input to the output.
What do you mean by mirror exactly? Like just it took the center crop of that that size, or how?
Yeah. So wherever pixels are missing, they just took like whatever pixels values were there in the original image, they just took them and put them on. I'll check with the exact implementation once, and
Sure,
I'll
sure,
let you
sure,
know on this.
sure, sure.
Sorry, yeah. Oh, yeah. So, oh, sorry. How does I? If I'm not mistaken, it is the former, because when we're working with segmentation, we're dealing with classes, right? So like isolated lumps doesn't really mean much, because that would be like an object detection kind of thing, like you said. So as far as I one class is a set, and the intersection over union of everything in those classes, all the pixels in that classes and all the pixels like predicted for that class, and all the ground truth labels for that class. Thank you.
Yeah, nice session, Abhirath.